Stick with me. All right. We are in a new exciting time in the class. We barely touched on things getting started last week with the world of these tiny little subatomic particles. Atoms are made up of protons, neutrons, and electrons. And we talked about how protons and electrons each carry a certain amount of electric charge. 1.6 times 10 to the negative 19th coulombs was that quantity of charge, and that protons have kind of stuck with this from Ben Franklin, that protons are positive and electrons are negative. There's nothing inherently positive or negative about either of them, but they were given by definition, they are at least opposite, and we have decided to call one of them positive and one of them negative. It's all relative to something else, so an electric field or something. So we're going to get into that world a little bit deeper. And by the end of tonight's discussion on chapter 19 material, we will have our first electronic device that we could hold in our hand. And then next week, it just gets totally crazy because we're going to be building circuits, and we'll have resistors and capacitors and batteries and wires and everything next week. This week, still a little bit of the conceptual stuff. Just to orient us, so we're here. This is the Canvas page for last week and this week. So last week we talked about chapter 18, and we're going to have the quiz on chapter 18 material tonight. As we scroll down, we will get to tonight, March 29th. We're going to talk about chapter 19, and we'll have the quiz on chapter 19 material next Monday. So we'll talk about chapter 19 tonight, and after that, the thing that comes up next is chapter 20. So you're always in a position where you can look back a little bit, do the current week, and then look ahead if that's kind of exciting to you to see what's coming up. Come on. All right. You have the ability to work on, oh dear, hold on one second. Okay, you have the ability to work on the labs. Last week's lab, or the lab that was doable by you after last week's coverage is lab number 6. Lab number 7 and 8 will be relevant to the material we talk about next week. So I do have high hopes that you'll do those labs, but a little bit early days yet for you to do those other two, but they're all there for you, and hopefully I will remember to do reminders so that you don't lose track of them. And then at the very bottom of the page here is the chapter 18 quiz that we'll do before we part ways tonight. I will see if you have any questions on chapter 18 before we get into quiz time. Okay, now to find the PowerPoint for tonight's presentation. Let us do reading view. All right. So chapter 19, electric potential and electric field. So it's hard for me to stop at electric potential. The full term that we will use a lot of times is electric potential energy. Um, and it's the potential energy that is exerted on electric charge due to an electric field that it's in. Right now, we are in a gravitational field. And if I go up to the second floor and hold a rock off the balcony, that rock has a certain amount of gravitational potential energy because it's in a gravitational field. And if I let it go, that potential energy will turn into kinetic energy. And it's the same kind of deal with electric fields, except that there is positive and negative. So we don't have, without getting too much into science fiction, we don't have antimatter. We don't have, anti-mass, something that you would hold out in the yard and it would shoot up into the sky because it's repelled by Earth's gravity. But with electricity, we have that phenomenon. So a lot of things are familiar, and then some things are different. So electric potential energy and electric potential. So like I was alluding to, the basketball, I guess in this instance, has a certain quantity of gravitational potential energy. A force is acting on it. That force is directed down toward the center of the Earth. It'll stop when it hits the floor. Doesn't have to go all the way to the center of the Earth. And the force is the mass of the basketball times the acceleration due to gravity here near the surface of the Earth. And then depending on its height, it has a certain amount of gravitational potential energy. Likewise, and so what we're depicting over here is two parallel plates with a certain amount of electric potential stored between them. So one side is the positive side. Remember, whenever we do this Q with the little 0, that's standing for a test charge, which for our purposes is some quantity of positive electric charge. And so this positively charged particle is repelled from the positive plate and attracted to the negative plate. And so anywhere that it might exist between the two plates, it will have a different amount of electric potential energy. Just like the basketball at different heights above the floor will have different quantities of gravitational potential energy. So the force that's exerted on our charge is the quantity of charge times the electric field strength. The electric field is measured in units of newtons per coulomb. And so if we have a certain quantity of coulombs of charge times newtons per coulomb, we get a force in newtons. If we move a charge around inside an electric field, we will have done work. Work is the change in potential energy. That's what it is if we're lifting up a box and we're changing the gravitational potential energy of the box. That's coming from us doing work. If a charge moves within an electric field, work has been done in order to do that. The potential energy per unit charge is also called the electric potential. So the work per unit charge, or the energy per unit charge, is called the electric potential. We are building up to something that I'm pretty sure you will have heard of. So A lot of hand waving right now, but we're going to get to something that is a little more familiar. And here it is. Electric potential is voltage. So you plug your computer into the wall. It is a 120 volt outlet. You have a battery that you hold in your hand that is a 1.5 volt battery. Unless it's a 9 volt battery, then it's a 9 volt battery. But a battery or a wall outlet, it's defined by the voltage, the electric potential energy per unit charge. So voltage is joules per coulomb. That's what a volt is, 1 joule per 1 coulomb. And then you have some idea of the magnitude of energy that a charge will have when it travels through an electric field with the potential difference of 1 volt or 1.5 volts or 9 volts or 120 volts. So we can quantify that. So the work done here by the electric force test charge, 2 times 10 to the negative 6 coulombs. If you're not really familiar and happy with doing scientific notation on your calculator, this stretch of the course is going to be very painful that way. And I don't want you to be in pain while you're trying to enjoy the amazing wonders of physics. So my calculator and most scientific calculators, I type in 2, and then there's a button that I hit for EE, and then I do 6 negative, and that will mean 2 times 10 to the negative 6th. If I don't have my calculator set into scientific notation, when I type in 2EE 6 negative, it will immediately report that that number is 0.0000456 but I also like to just set my calculator to scientific notation, so that's less confusing to me. Mine is a TI-30X something. Whatever your calculator is, there is a way that it will do scientific notation for you flawlessly. Do try to follow along if I do worked out examples in class, or when you do the homework and there's the homework videos, just make sure you can plug the numbers into your calculator and you get the same answer that I do. Then you'll know that your calculator is set and working correctly. And as always in life, whatever specific model of calculator you have, there's probably a YouTube video that will walk you through how to do basic scientific notation, trig functions, whatever else on your specific calculator. So don't go into a quiz or an exam unsure of that part of what you're doing, because that's a bummer. So find the difference in electric potential energy between the 2 points. So voltage and voltage. So it's electric potential energy per unit charge or work per unit charge. So here what we want to do, we have energy in joules. We have the unit charge. So joules per unit charge, so positive 5 times 10 to the negative 5th joules divided by positive 2 times 10 to the negative 6th joules. When I do that on my calculator, 5EE 5 negative divided by 2EE6 negative, I get 2.5 times 10 to the first, which is also 25 what? Oh, I'm a dope. Joules per Coulomb, 25 volts. Sorry about that. The quantity of charge is in coulombs, so joules per Coulomb, and the units is volts. I may have told you the story before that I will frequently have students from geological sciences take physics, and characteristic of students in that major, more than other majors that I've seen, they will follow the units, even if they don't know the right equation to use, and even if they are confused about what's going on in the problem, they would say, oh, wait, this is potential difference. Potential difference is in volts. So if it's going to be volts, that's got to be joules per Coulomb. And they might never look at the equation sheet, but they would know to divide joules by coulombs in order to get the answer, because that gives the right units. That doesn't always serve you well. And I give you the equation sheet, so I recommend you look at it. But that can work so often in life to get you the right answer. We wanted to go from A to B. A is high potential, B is low potential. So it's always final minus initial. So the final electric potential energy is lower than the initial. So it's -5 times 10 to the 5th joules change in electric potential energy, and then -5 times 10 to the -5th divided by 2. So I didn't pay attention to that part when I was doing the example because I was working on scientific notation, but it is lower electric potential energy, so it's a lower electric potential as you get closer to the negative charges for our positive test charge, because it's repelled from the positive plates and attracted to the negative plates. So it's going to be less stress, less energy involved the closer it gets to the place that it wants to go, like a ball rolling down a hill. So here's where it gets weird. My son is taking AP Physics in high school right now. And when he's doing his homework, my wife is listening to him do his homework more than she ever listens to me teach my classes. And she is losing her mind over why physics is so crazy that we call, electrons negative charges and protons positive charges. And, then you have a perspective on everything. So don't let it make you crazy. Just kind of go with the flow. For an electron will have lower potential energy at the place we call higher electric potential, because the electron is attracted to the positive charge and repelled from the negative charge. Just the opposite of what we just did, where we had a positive charge that's repelled from the positive plate and attracted to the negative plate. So electrons and protons are just the opposite in what they do, but we're still going to refer to everything from the perspective of protons as though the protons are moving around. So we have a region of high potential, and that's the positive terminal of the battery. And it is the protons that would be repelled from that high potential. It's the protons that would have high electric potential energy in the positive region and low electric potential energy in the negative region. Just the opposite of electrons. Now, why this can be so frustrating is because in reality, in a battery, it is the electrons that are moving, not the protons. So everything kind of goes backwards from the way that we describe it. Don't let that bother you. Just accept it. So positive charge accelerates from a region of high electric potential toward a region of lower electric potential. The negative charge, the electrons, would accelerate from the region of low potential toward the region of high potential. So toward the positive terminal of a battery, for instance, with a potential difference between the two terminals of 1.5 volts. It can be a little much. So speaking of a little much, is putting everything in context, everything from the whole stinking physics 1 and 2 experience. So total energy of anything, electrons, protons, molecules of water, people, cars, anything at all. The total energy is the sum of the kinetic energy, 1/2 mv squared. Anything that has mass and is moving has kinetic energy. And then if it's rotating, I don't know if you remember this from toward the end of physics 1, 1/2 I omega squared, this is rotational kinetic energy. So even if it's not moving linearly, if it's just spinning around on an axis, if it has mass, it has a moment of inertia, typically mr squared, how the mass is distributed around the axis of rotation. And then omega is the angular velocity in radians per second. Those two things together account for some of the energy that a molecule has, but it might also have gravitational potential energy, mgh. Oh my goodness, remember this, Hooke's law? If you have something that's vibrating back and forth on like a spring or an axis, or if you have two oxygen atoms that are bound by covalent bonds and are vibrating back and forth, there's another form of energy there. That's the 1/2 kx squared spring potential energy. And then added to all of these things is also now this electric potential energy. If the object has charge and is in some kind of electric field, that's another form of energy. So we're keeping all of these generally in mind as we encounter the world, and it's getting more and more complex. Usually, some things are important and other things aren't in different situations, so you don't typically have to worry about the electric potential energy acting on a baseball that somebody threw, but the other forms of energy might be really important. And then you don't typically have to worry about the rotational kinetic energy of, ion of, I don't know, H3O plus, a charged particle of water. You typically don't have to worry about the rotational stuff as much as the electric field doing something. There's also this other world. I invite you to join me in studying in the world of physical chemistry. It's very fascinating, but in case you don't choose to go down that road, I'll just let you know that there is this thing that we talk about in talking about how much energy is going on in a certain situation, and we call it the electron volt. And it's the energy of an electron when it moves through a potential difference of 1 volt. So an electron volt is actually a measure of energy in joules, not volts in joules per coulomb because we're talking about an electron, 1.6 times 10 to the negative 19th coulombs going through 1 volt. So that's just a thing that I guess we had to mention. All right, so looking at some kinds of problems that you might see in some sort of context, a particle has a mass of 1.8 times 10 to the negative 5th kilograms. That's really tiny, but maybe this is in a mass spectrometer or something where you're doing something to figure out some quality of the particle as it exists in there. And it has a charge of 3 times 10 to the negative 5th coulombs. It is released from point A and accelerates horizontally until it reaches point B. The only force acting on the particle is the electric force, and the electric potential at A is 25 volts greater than that at C. What is the speed of the particle at point B? And if the particle had a negative charge and were released from point B, what would its speed be at A? So sounds like a whole lot of blah, 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 blah. But what we're looking at, we want to figure out something with speed. Speed is going to be the result of kinetic energy. So when we give it energy, kinetic energy, oops, bad E, 1/2 mv squared. So 2ke equals mv squared. V equals the square root of 2ke divided by mass equals. So if we can figure out how much kinetic energy it has, we can figure out its velocity. So we have a certain amount of charge, we have voltage, so volts is joules per coulomb, and we're looking for joules. Volts is joules per coulomb, so joules equals coulombs times volts. So charge in coulombs times volts would give us the energy in joules, and then we'll plug that in for kinetic energy. We know the mass that was given. We can figure out what's going on here. So even if you're like looking at a question and you're like, oh my gosh, I have no idea what to do here, take a minute and try to think through the different parts of the problem to see how they might fit together. So, sorry about that. Should have muted. So 25 volts times the 3 times 10 to the negative 5th coulombs, square root of that, that's joules, divided by the mass in kilograms, and we get 9.1 meters per second for the velocity of the particle at that point in space. It's still kind of weird hand wavy stuff, and I appreciate that. Again, it will get to very specific electric current running through a light bulb and generating heat and light. That's coming up soon, but we got to set this stage first. If we want to figure out the potential of a point charge in space, we can do that. K, remember, is our coulombs constant, 9 times 10 to the 9th Newton meter squared per coulomb squared. I don't have the right equation sheet here. We'll double check that. Times coulombs divided by the radius, we can figure out joules per coulomb for a charge just where it's located relative to other charges in space. So the potential of a point charge will depend on how far it is away from other fixed charges in space. And so we can look that it changes, you know, because it's relative to its distance. So if we go further away, it's going to approximate 0, but wherever we are here, 1.2 meters away, they're saying it's positive 300 volts, or for the opposite charge, negative 300 volts, but eventually going down to 0. So when we deal with point charges in proximity to a fixed charge, we're able to map out the electric field around them. So we did some stuff last week when we're talking about a positive charge and a negative charge, and that the electric field lines would, gotta get it, positive charge, negative charge, and electric field lines will go from positive to negative. And the bigger the charge is, the more electric field lines we have. And this is essentially mapping out the trajectory that a positive charge would take if it were stuck in this kind of field. Now, we are looking at a slightly different concept, but the same general theme, that if you have fixed charges in space, we can look at the potential at that point, any point in between them. We don't need to do all of the math. What we want to get to is this idea that there are equipotential surfaces, that at some distance from a charge, every point in a sphere, 360 degrees around any trajectory, would be the same potential. So we call that an equipotential surface. And we would depict that. The electric field lines would be cutting through those perpendicular to the plane at any point, and the surfaces would be in the middle. So this is kind of our depiction of the positive and negative charge. The electric field lines go toward the negative, away from negative toward positive. But then the equipotential surfaces exist at different distances away from the charges. And, you know, I don't know what they're mapping out here, a drop of, you know, 100 volts each time or something, but that's electric field. It's kind of like if you've ever seen a map, if you're like mountain climbing or something and you want to know how high up the mountain is, but you're looking at a two-dimensional map, you might see rings like this that are depicting, you know, every ring is up another 100 feet or something. So you get an idea of how high and how steep the path is. All right. So we have equipotential surfaces. We have these two parallel metal plates, one with positive charge, the other with negative charge. The energy difference between the two plates is going to be the voltage difference divided by, the electric field is going to be the voltage divided by the separation distance between the two plates. So volts per meter is electric field. This is a good one to know. It may come in handy sometime. Electric field is both volts per meter, as well as joules per coulomb. So volts per meter, that's an M, I'm sorry. E equals V over M equals joules per coulomb. And that can be very, no. Joules per Coulomb is volts. Newtons. Oh, hold on a second. Hopefully I say it on the next slide, so we're not going to be more confused. Volts per meter, that's true. All right, I will get back to that. Hold that thought for just a moment. When we have the two parallel plates, like we've been discussing, that can be a thing, an electronic device. The electronic device that would be is called a capacitor. A capacitor, in a lot of situations, behaves like a battery, but it's different from a battery, but it holds an electric potential difference for some amount of time until it's triggered and it goes. So Q is quantity of electric charge in coulombs. Capital C stands for capacitance of the capacitor, which is coulombs per volt, which we use the term farad for. So capital F, coulombs per volt. And then V is voltage in volts, which is joules per coulomb. So we're not going to make capacitors ourselves, but just so you know, capacitors are two metal plates with something in between them. The closer you can force the two plates together without the charge hopping, the better capacitance you have, the more charge, usable charge you're able to store. If you ever encounter really old capacitors, they used to put paper, literal, made from wood pulp paper between the two metal plates. The problem with that is that when the charge does hop, there can be a lot of heat and paper can catch on fire. So there's a whole world of materials science where people have come up with different materials to put between the plates that will serve the job, but not catch on fire. So here's certain dielectric constants. We don't need to do any calculations with these. That's not what I want you to worry about. Capacitors have all sorts of jobs, some of them in our computer keyboard, some of them in our delayed windshield wipers, some of them in camera flashes, all sorts of different times, and like pacemakers. And if you or someone you love has a heart condition, and they will build a capacitor or insert a capacitor in to give your heart a little reminder to beat at a regular basis. So that's all there. So the energy that is stored by a capacitor is 1/2 times the capacitance of that capacitor times the voltage, the battery kind of thing that's hooked up to, voltage squared. We're not going to have to build capacitors, so we don't need to worry about these other things. But the first one, the amount of energy stored by a capacitor, is an important thing. I think this image of trying to start somebody's heart, and again, that's capacitors. There used to be a time in life where camera flashes, when cameras were a separate device, not your phone, and there was a flash that went on top of your camera, and when you turned it on, you heard this sound, whee, as it charged up. If you're trying to jumpstart somebody's heart, you would build up a certain amount of charge and then clear and boom. try to get their heart beating again. And I think this guy on the airplane kind of looks like a young Barack Obama. I don't know, just strange likeness. As we talk about electric signals, you think about batteries and computers and cell phones and flashlights and other devices that run off of electricity. But don't forget, so do we. And we have nerves and we have these ion channels in our cells, and everything, every signal in our body is being sent through electrical signals. And so this is common to everything. We don't need to do all of this. There's another thing coming up, I'm sure of it. Hold on, don't stop listening yet. So here's the deal. Capacitors are this thing where if you have lots of capacitors and you hook them up in series, you get less total capacitance. So capacitors, oh, I need my writing power. Capacitors in series is 1 over C1 plus 1 over C2. Sorry, I got to fix this. 1 over, oh, forget that. 1 over CS equals 1 over C1 plus 1 over C2 plus 1 over C3. So if I have 3 capacitors and they each had a capacitance of 5 farads, that's an odd number, but just stick with me. Each one had a capacitance of 5 farads. Then the series capacitance of hooking them up one after the other, 1 over CS equals 1 over 5 plus 1 over 5 plus 1 over 5. 5, 1 over, plus 5, 1 over, plus 5, 1 over. That number is 0.6 because it's 0.2 plus 0.2 plus 0.2. But that's not the answer. The total capacitance then is 1 divided by 0.6. And that is 1.67. So I took 3 capacitors, each with a capacitance of 5 farads, and I hooked them up in series, one after the other after the other. That means that the total voltage difference between the 2 terminals of the battery is divided up over all 3. And we know that capacitance is dependent on the voltage. So if we divide the voltage up, we're ending up with a lower total capacitance, as opposed to the situation where you take 3 capacitors, and you hook them all up in parallel. When they're parallel to each other, each capacitor sees the full voltage of the battery, even if it was there all by itself. And so when you put them together, again, if I did my weird 5 farad capacitor, it would be 5 plus 5 plus 5. That would be 15 farads of total capacitance if I have 3 capacitors hooked up in parallel. So series and parallel is something we'll see again with resistors coming up in the next chapter. But this is our first introduction to that concept and a device that you can hold in your hand, a capacitor. Clear, close. And so we're building up to electronic devices and capacitors and defibrillators and cell walls and all that stuff. That takes us to the end of chapter 19. Ooh, okay. Catch your breath. And come on. We will just take a few moments and take a look at the chapter 18 homework. And then I'll get you, answer any questions you have and get you oriented for the quiz tonight. So let's just take a couple of minutes and you think about any questions you have, and then we'll get started. I'll be right back. All right, coming back again, and I'm seeing questions in chat, and that is good. So just to orient us again, very large number of charged particles in most objects. Why aren't they always exhibiting static electricity? Because everything is made up of protons, neutrons, and electrons. And usually there is a balance between the number of protons and the number of electrons so that things are electrically neutral. But we can, with actual physical rubbing one thing against another, get an imbalance. Some things are more electronegative, so we'll grab the electrons, other things aren't, and so we'll have an imbalance. And so this temporary imbalance, some things exhibit positive charge and some things exhibit negative charge. Okay, so I see number 28 right now. We'll jump down there and then we will we'll see if there's anything else. So what is the magnitude and direction of the electric force exerted on a 3.5 microcoulomb charge in a 250 Newton per Coulomb electric field that points due east? So if the field is pointing east, we have north, south, west, and east. So the electric field of 250 newtons per coulomb is pointing that way, I guess to the right on my page. The electric field is newtons per coulomb. I want to know the force, magnitude and direction of the force. So over here is positive, here is negative. I have a 3.5 microcoulomb charge in that field. So it just says 3.5 microcoulomb. So I'm assuming it is a positive 3.5 microcoulomb charge. So the force is Q times the electric field, QE. So 3.5 times 10 to the negative 6th times 250 newtons per coulomb times 10 to the negative 6 coulombs. So clear 3.5 times 10 to the negative 6th times 250. And I got to get back into scientific notation or it's going to look messy. 8.75 force is 8.75 times 10 to the negative 4th, that's a 4, newtons. Or if I took it out of scientific notation, 0.00 F equals 0.0000875. This is a positive charge. The positive charge is going to be repelled from the positive side. So it would be due west. It would be the opposite direction of the electric field that is being depicted here. So electric field is pointing from negative to positive. Positive charge would move from the positive region to the negative region. All right. Remember, electrons have mass, not much, but a little. Protons have mass, more. So if you give something a negative charge, what you have done is you've taken something that is electrically neutral with the same amount of positive and negative charges, and you've removed some of the electrons. So give positive charge, remove electrons. And so it would be positive, positive, minus. It has a net positive charge, but it has one fewer electrons. Whereas if I give something a negative charge, it would be positive, negative, 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 positive. By giving it a negative charge, I've given it an extra electron. If the field points east, that is negative to positive. So if I said that wrong in the homework video, I apologize. But this is a positive charge. It would be the opposite direction of the field vector. I will have to look at that. I have made some mistakes in the homework videos, but I made them a while ago and I don't always watch them over again before we cover it in class to know if I made a mistake. Let's see. So the force, we use Coulomb's law constant when we're figuring out a force. So force equals K Q1 Q2 divided by R squared. Got to do everything in the base units. So they have equal charges of negative 30 nanocoulombs. So 9 times 10 to the 9th Newton meter squared per coulomb squared times negative 30 times 10 to the negative 9th, oh, that's a 10 to the negative 9th coulombs times negative 30 times 10 to the negative 9th coulomb. So I can do that squared because it's equal charges, divided by R squared, 8 times 10 to the negative 2nd meters, that's a centimeter squared. And so you run the numbers and you just got to be careful when you're doing the scientific notation because numbers can look bizarre. If there's a really big number on the quiz, it is just a pain in Canvas to report a really large number. So I've said, just take that really large number. So if the number was up here, 1 times 10 to the 12th, I say take that 1 times 10 to the 12th, 1 EE12, and divide it by 1 times 10 to the 10th. And that would be 100. So just if you have a really huge number, I've given you a way to tell me the answer with a much more reasonable number, just because it's a pain. All right. Any other questions before the quiz? And a couple of good ones there. Just to orient you on the quiz when you go to take it, I've given you a data sheet that has the mass of a proton, the mass of an electron, volts is joules per coulomb, change in potential energy is quantity of charge times the voltage, the value for K in the Coulomb's law constant, the quantity on an electric charge. It has these brackets here for absolute value. Electrons have negative 1.6, protons have positive 1.6 times 10 to the negative 19th coulombs. Any other questions before the quiz? I will stay here with you on chat. So ask any questions you have while you're working on it. I'll keep the quiz open so I can check what questions you have. And if I don't think there's any graphics that you won't be able to see. So I think you're good. All right, have the quiz. When you're done with the quiz, you may go for the evening. I'll post the video sometime soon. Gonna stop recording now.